Hi again, everybody. In this video, we're going to talk about symmetry. Now, there are three types of symmetry that we're going to talk about. A graph can have symmetry about the y-axis if for every point xy on the graph, the point negative xy is also on the graph. If we think about that visually, for any point xy, the point negative xy is on the graph, we get this y-axis symmetry. If this is x2, y2, then negative x2, so the opposite x value, the same y value is on the graph, and we get this, like, if this is 2 units away, let's say this is 2 units away. If this is 1 unit away, this is 1 unit away. We get this symmetry over the y-axis, so that's why it's called y-axis symmetry. We have symmetry about the x-axis, similar reasoning. If for every point xy on the graph, the point x negative y is on the graph. And then we'll get that symmetry. Instead of being over the y-axis, it would be over the x-axis instead. And then we have origin symmetry. Now, origin symmetry is that for every point xy on the graph, the point negative x, negative y is on the graph. And so the symmetry actually happens through the origin. And so that's why it's called origin symmetry. Now on a graph, this is pretty easy to spot. But what if you're just given an equation and you want to know whether it has x-axis, y-axis, or origin symmetry? Well, let's go through an example. And for each of these, we will test all three. Okay? So let me write down our first equation. Okay, and we're going to test our x-axis symmetry. We're going to test our y-axis symmetry. And we're going to test our origin symmetry for this one equation. So to test x-axis symmetry, we go back and look at the definition. X-axis symmetry says that for any point xy, the point x negative y is on the graph. So what that really means is if I plug negative y in for y in this equation, I should be able to get back the original equation. And I'll show you what that means. So x squared plus, it was normally y, but I'm going to make it negative y squared equals 4. Now, when I square negative y, I get negative y times negative y, which is a positive y. And so that gives me positive y squared equals 4. And so I've gotten back the original equation. And so there is x-axis symmetry for this graph. Likewise, if I check y-axis symmetry, instead of replacing y with negative y, I'm going to replace x with negative x. And for the same reasons that we had x-axis symmetry, it appears that we have y-axis symmetry as well. Check. And now let's go for origin symmetry. We have for every point xy, looking at the definition, for every point xy on the graph, the point negative x, negative y is also on the graph. So let's plug in negative x for x and negative y for y. And it looks like we get back the original equation. And so this graph has all three types of symmetry. Does anyone know what the graph x squared plus y squared equals 4 looks like? Well, we're going to talk about it in the next video, but for now, I'll just, spoiler alert here, this is the graph that gives me a circle, and the radius of that circle is 2. So it's a circle on the origin, and that's why it has all three types of symmetry, because a circle can be split any way, and you get symmetry. But now let's look at an example that doesn't necessarily have all three types of symmetry, or maybe it doesn't have any of them. Let's move on to y equals x cubed. And again, we're trying to assess whether it has x-axis symmetry, whether it has y-axis symmetry, or origin symmetry. So for x-axis symmetry, we're substituting in negative y for y. So in this case, we'll get negative y equals x cubed. Now, I'm not squaring this negative y, and so there's no way to get this negative y to be positive again. If I try to make it positive again, I'd have to multiply both sides of this equation by negative 1. And if I multiply both sides of this equation by negative 1, I get my y back, but now I have negative x cubed, which is not the original equation. So there's no x-axis symmetry here. Let's try y-axis symmetry. Okay, so now I would replace x with negative x. But negative x cubed is negative x times negative x times negative x 3 times, which actually gives me negative x cubed. And that is not the original equation. So there's no y-axis symmetry here either. So let's try origin. So we replace we replace y with negative y. We replace x with negative x. So there's a negative y on this side of the equation. On the other side, we just went through this. This turns into negative x cubed. And so now I can multiply both sides by negative 1, or divide both sides by negative 1, however you feel. And y equals x cubed, which is the original equation. And so this does have origin symmetry. So what I'd like you to do now is I'd like you to go through that same process. I'd like you to pause the video and try to find out all the different symmetries for y squared equals x. And then when you come back with the video, I'm going to work through it, and you can check to see if you got it right. Okay, so why don't you pause the video now. All right, I take it you're back. So let's go ahead and try to find the different symmetries for y squared equals x. We're looking for x-axis, we're looking for y-axis, and we're looking for origin symmetry. So x-axis symmetry, we're going to replace y with negative y, which when we square it gives me y squared equals x, which is the original, so we do have x-axis symmetry. Y-axis symmetry, we're going to replace x with negative x. In that case, I still have y squared equals negative x, which is not the same as the original, so this doesn't work. And then we try it with origin symmetry. We replace both of them. On the left side of the equation, we get a positive y squared. On the left side or right side of the equation, we get negative x, which is not the original. And so that doesn't work either. So we only have x-axis symmetry for this problem. All right, so let's look at the graph of a circle. We have the fact that the graph of a circle comes from the distance formula. Remember what we talked about earlier in the previous video, that the distance formula comes from Pythagorean theorem. And if you think about a circle, right, the definition of a circle is that it's the shape that's formed from all of the points that are the same distance away from a fixed point. And that fixed point is the center of the circle. And so let's say this is the center of my circle, and this is a terrible circle, but I have a circle going around it. Okay. This distance right here, I'm just choosing an arbitrary point on the circle. And this is the center of my circle, and we denote the center of a circle with the point h comma k. Okay, so this distance right here would be x minus h, squared, because it's the difference in the x coordinates, plus the difference in the y coordinates, equals the hypotenuse, this distance, squared. But that distance in a circle is not called d, it's called the radius. And so there's your formula. Now let's put this to work. We're going to graph these equations, okay? We're going to start with x plus 2 squared plus y minus 3 squared equals 4. Let's first identify what the center of the circle is and the radius of the circle. Looking back at the definition, it's x minus h, which means that if there's a minus sign, then the minus sign is built in. So if there's a minus sign already there, that means that h is just the positive number, or k is just the positive number. If there's a plus sign, that means we really had y minus some negative number, and the negative became a plus. And so if we see a plus in the parentheses, that means that the number I'm looking for, the coordinate I'm looking for, is actually negative. So we can see that this is really x minus negative 2. So negative 2 is the x coordinate of the center, and 3 is the y coordinate of the center. And the radius in the equation is being squared. It's right here, it's squared. And so the radius here is really 2. We have to square root in our head what this number is to get our radius. So we go to graph this. We have a center at negative 2, 3. This is terrible placement of my coordinate plane. Okay, so we have our x-coordinate, our x-axis, our y-axis. We're going up by ones, okay? So this is negative 2, 3. This is the center of my circle, okay? Negative 2, 3, and the radius is 2. So I'm going to go 2 to the right, 2 up, 2 to the left, 2 down, and I'm going to do my best to make a circle. I have a little tool here that's going to hopefully help me out. I can do better. Way better. Okay, and there's my graph. Now I'm going to do the other graph on the same coordinate plane, but why don't you pause the video and do this example on your own. First, identify the center and the radius, and then graph it. Go ahead and pause the video now. You're back? Good. The center is 0, 0, because there is no h or k shown, so that's 0 and 0, and the radius is 1. So we go to graph this. Here's the center. The center is actually not part of the circle, so we should technically erase that once we're done. And then we graph our circle. Oh, beautiful. We can erase the center, which also erases our coordinate plane. And you do, oh, sorry. Do you know what this circle is? So this is called a unit circle. It's called a unit circle because it has a radius that is 1 unit. 1 unit is the radius. And it's centered on the origin. So this is called the unit circle, and that's what this book is all about. The book that you're doing this out of is called A Unit Circle Approach to Trigonometry, or to Precalculus. And so that's what we're going to talk about a lot during these times. I'll see you in the next video for the last part, and that's writing equations of circles given information.